Hey guys, this is Mr. C here, and in this video we are going to be simplifying some radical expressions. And so I've got a few examples I'm going to show you to kind of generalize it for most of the expressions you're going to see. And we're going to start out with something like this. We're going to do the square root of 20x squared. All right. When you're simplifying an expression and you have a bunch of stuff under here, variables and numbers, what I like to do first is I like to go ahead and simplify the number part first. So 20, and I need to break that down using a factor tree, or if you already know it. But 20 is, let's just say 4 times 5. 5 is prime, and 4 is 2 times 2. Then we have 2 x's. So here's one way that we can do this. We can actually take all of these factors and we can write them underneath the square root here. And it is a square root because there's no index here, it's just a 2. We can put a 2 there if we want. So 2, 2, 5. And then we've got 2 x's, x squared. So x and x. And so we're going to go ahead and draw that all under the square root. Now, when you're simplifying a square root, we remember that a pair on the inside of factors of the same kind is worth 1 on the outside. So what I'm looking for is pairs. And the first thing I see is a pair of 2's. So that pair of 2's is going to come out as a single 2 on the outside. The 5 doesn't have a pair, so it's going to stay in. But the pair of x's are going to come out as a single x on the outside. The 5, since it didn't have a pair, is going to be still left under there with just the square root of 5. And so when you get done here, taking everything out you can, you're going to multiply everything in front together. 2x root 5. Okay, this is my answer, and it's an answer that I would accept all day long. A purist would, though, say, well, you had 2 x's in here and it came out as 1 on the outside. To make that true for all real numbers, then this x right here has to be the absolute value. So you could, if you looked in the back of a textbook, you would see probably this answer. Okay, and technically I should probably do that. A lot of times I don't, because I just assume x is greater than 0. And in most tests, like the ACT or maybe EOC or something like that, they're going to tell you that x is greater than 0. But if x is allowed to be negative, then technically you do have to have the absolute value bars around the x, because it was 2 of them on the inside squared, and on the outside it's just 1, and you only consider the positive one, and you got to make it positive. But I don't want to confuse you. This answer right here I would be okay with, and I'm going to generally stick to that. And in these examples, I'm going to assume that x is positive in every case. All right. So let's take a look at another one. And this one, we're going to have the square root of 153 x to the 4th. All right, so now, again, assuming x is positive here, first thing we need to do is break this number down, 153. And so if you take 153 and you want to figure out what you can break this down into, try first adding up all the digits. 5 and 1 is 6, plus 3 is 9. Since it's divisible by 9, the sum is divisible by 9, that means 9 goes into it. Without getting into the number theory that's involved, it's true. That's one of your divisibility rules. So if you divide that by 9, you should get 17. Now 17 is prime, and so I always circle my primes, and 9 is 3 times 3. And so I can rewrite this as 3, 3, 17. You don't have to go in order like this from least to greatest. They just have to be listed in here. But I usually find myself doing that. And I need 4 x's. 1, 2, 3, 4. And since now it's gotten a lot longer here, so I'm not too sloppy, which I tend to get, I'll use a straight edge and make that look good. All right, now here's what we got. We have a pair of 3's. So that 3 is coming out. 17, just one of those. I've got a pair of x's, and I have another pair of x's. All right, the 17, there's only one, so it stays in there inside the square root. And there it is. So my final step is to multiply all of this together and clean that up. So I have 3x squared root 17. Some people say on the square root of 17. It doesn't matter. I usually just say 3x squared root 17. That's fine. But that answer is correct. Some people also may put a little dot there. And if they put that dot there, all they're doing is separating this from this so that 2 doesn't kind of creep over and start going with this radical, because in other problems it might not be the square root and you might lose this for somebody thinking it's right there. So we want to separate those two out and make sure that we know the 3, the x squared, and the root 17 are all separate factors of this expression. All right, so that was a good example. Let's try another one. This time, we're going to do the square root of 361 and then x cubed. All right, so let's see what that's going to look like. 361. If you take 361 and you add up all the digits, you get 10. That's not really going to work too well. So I know it's not even. I know 2 doesn't go into it. I know 5 doesn't go into it. Here's one little trick that you can do. It's called the Theorem of Aristophanes. You can take the 361 and take the square root of it. If you take the square root of it, it's 19. Now, luckily, I just found out, just by chance, that 361 is 19 squared. And I probably wouldn't have known that right from the start. And it's okay to use a calculator on these. You know, nobody's going to get upset if you do. So 19 and 19 will work. So we're going to do 19, another 19, and then 3 x's. X, x, then x. Okay? Again, I don't want to be sloppy, so I'm going to go ahead and use my straight edge to do this part. Sometimes this gets quite lengthy, and that's okay. Okay, let's look for pairs now. So equals. I do see immediately a pair of 19s. So that 19 is coming out. I see a pair of x's. That x is coming out as a single one here. But that x is all by itself and it does not have a pair. So it's going to stay under the square root. So cleaning this up, I have 19x, and I'm going to put times the square root of x just to separate this so nobody thinks that anything part of this is included in the square root. All right, that's a good habit to get into. All right, let's do another example here. Okay, this time we're going to change it up. We're going to do the cube root of 81 x to the 9th. Now, here's the problem here. I have 9 x's, and I am free to write them all out if you want to. If you want to do that, you can. Let's take the 81. 81, 9 times 9. Okay, now, since it's a cube root now, not a square root, I need to keep breaking it down. So these 9s have to be broken down into 3s. 3, 3, and then 2 more. Okay, and visual learners really need to see all of this just like this. So 4 3s, 1, 2, 3, 4, and I'm going to write out 9 x's just to do it. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, I'm going to give you an option here too, here in a minute. For those of you that don't want to write down all those x's, that's still going to work just fine. Whoops. Okay, let's make that look good. All right, now, here's what I've got. I've got a cube root sitting here, not a square root, but a cube root. This is called the index. The index of this radical tells me how many of these in groups I need to take out so that 1 will come out. So with a square root, it's 2. With a cube root, it's a group of 3. So I need 3 3s to come out as a single 3 on the outside. This extra one is staying. Okay, I've got a group of 3 x's. I've got another group of 3 x's. And I've got another group of 3 x's. And I've used up all of my x's. The only thing left is just that 3 right there. So now, that extra 3 has to stay under that cube root again. Be very careful because a lot of students will forget to put that little 3 there, and your teachers and professors will count off of that. All right, so we're going to clean that up, and we're going to put 3x cubed times the cube root of 3. That might look pretty complicated, but after a while, and after doing these for a while, it's really not going to seem very complicated at all. You're going to get things that are much more complicated than this when you get to Algebra 2 and Pre-Cal and above there. All right, so I'm getting back to how I can do this a different way. Let's try this one more time a little differently. So this time, I'm going to keep the same problem. Cube root of 81 x to the 9th. But this time, I'm going to do a little differently. I'm going to take the number and I'm still going to break that down into its primes. And I have the tendency to do that. But this time, I'm going to take that x to the 9th and I'm going to leave it as x to the 9th. Okay, and it's still cube root. So now I'm going to go ahead and, I believe they call this the vinculum, right there. All right, so here's what I do now. I have a group of 3 3s, just like before. So that 3 is coming out. Okay, that 3 is left in. And here's how you deal with these variables now. How many groups of 3 can you take out of 9? Or better yet, how many groups of 3 without going over 9 can you divide out of 9? Well, 9 divided by 3 is 3. You can get 3 groups of 3. It's kind of like going all the way back to elementary school when you have to divide things out with manipulatives. But there are 3 groups of 3 in 9. So therefore, it's going to be x cubed. And that represents the 3 groups of 3 x's. And then you've got your cube root of that extra 3 still sitting there. And you still get the same answer, but you get a lot quicker. So students, what I suggest is to start off with this, okay? And then after you start getting comfortable, then start venturing into this kind of territory, because this is more abstract and it's generally faster, and it'll become more understandable when you do a bunch of them. All right, but you can do it either way. Okay, let's take a look at another one. This one is going to be the cube root of, and this time we're going to do 24x squared. Okay, so our number is really not too big. Let's go ahead and break that down. 24 is 8 times 3. 3 is prime. 8, we already saw, is 3 2's. And I like to do it this way when I see that I have a perfect cube. It's quicker. So I have the cube root of 3 2's, 2, 2, 2, a 3, and then 2 x's. Okay, so we'll draw our radical up here. All right, I need a group of 3 to come out, and the only group of 3 of anything that I see are these 3 2's right here. So those 3 2's are going to come out as a single 2 on the outside. These guys just get multiplied back together, and they're going to go into the cube root that's still left, 3x squared. And that is it. So that's your final answer. It looks complicated, but that's exactly what we want as our final answer for that one. All right, this time we're going to do the cube root of 150 x to the 4th. Okay, so let's see what this one looks like. Equals. All right, let's break down 150. Let's do 15 times 10. 10 is 5 times 2. Okay, and 15 is 5 times 3. Okay, so we have a cube root of 2, 3, 5, 5, 2, 3, 5, 5, and then 4 x's. 1, 2, 3, 4. All right, let's draw our line on top. Okay, so we need a group of 3 of anything that we can see. Nothing here, nothing there. There's only 2, not 3 of them. But we do have 3 x's that we can choose. And so if we choose these 3 x's right there to come out, we have a single x on the outside, but everything else is going to get multiplied back together and left under that cube root. There's nothing you can do with it. Well, 2, 3, 5, and 5 was 150 to begin with, and then it turns out that that 150 is still going to be there. That single x that's left right there is going to be with that 150. And that is all you can do right there. That's it. That's got to be your final answer. Okay? Let's take a look and see what happens now when you have several variables underneath the radical. So this time we're going to do the square root of, let's do 216 x cubed y to the 4th. We're going to see that it's really not any different than what we've been doing already. So let's break down our 216, which I already know what that is, but we're going to break it down anyway. 216, let's divide it by 2 first. Okay, if we take 216 divided by 2, 216 divided by 2 equals 108. Okay, let's take 108 and divide it by 2. Divided by 2 equals 54. Take 54 and divide it by 2. Divided by 2 equals 27. 27 is a perfect cube. That's 3 times 3 times 3. And so we're going to draw 3 little lines here. 3, 3, and 3. 3 x's, 4 y's. So let's see how that's going to work. I really don't want to write all of these out. So I'm going to avoid that for now on this one. But I am going to write all the numbers out. 2, 2, 2. And then 3, 3, 3. The reason why I know that it's going to be this right here, 6 times 6 times 6, is because that's the sample space you get when you roll a die 3 times. But that's what happens when you do this a lot. These numbers start to come up over and over, and then times y to the 4th. And see, that I would have run out of room if I would have written all the x's and y's out. So sometimes I don't want to have to do that. All right, it's a square root, so I want pairs. So I got a pair of 2's. So I got a single 2 that's coming out. I got a pair of 3's. So I have a 3 that's coming out. So that 2's left in, that 3's left in, right? So let's go ahead back here. Let's try our square root of 2 times 3. Those 2 are right here. These 2 came out. Leaving some space here for the x's and y's. Well, the index is 2, square root. So how many groups of 2 can I take out of 3? Well, it's 1, right? So 1 x comes out, but there's an extra x to make 3 that's still there under the radical, because I only took 2 out to create that x right there. So I've got 1 extra 1 that needs to stay under the square root. However, for the y's, I can get 2 groups of 2 to come out and take care of all of those 4 y's. And so what happens is you get a y squared sitting there, and they all come out. So whenever that is a divisor of this exponent, all of them are going to come out. All right, so let's see how this works. Okay, so we've got 2 times 3 is 6. X, y squared, times the square root of 2 times 3 is 6, x. Again, it looks complicated, but the more of these that you do, the easier it's going to get, I promise you. And it's really not going to seem that bad. All right, so let's try this one. This time we've got the cube root of 135, x to the 12th, y to the 7th. Okay, so a lot of stuff going on here. Main thing is that you break down that 135 correctly. So it is divisible by 9, because 5 plus 3 is 8, and an extra 1 is 9. So I know 9 goes into it. I know 5 goes into it, which means 45 goes into it. But I'm going to check, I'm just going to do 9, just to play it safe. So we're going to do 135 divided by 9 equals, and we get 15. Okay, both these are composite, so we're going to break those down one more time. 3 and 3 for the 9, 5 and 3 for the 15. Okay, and so it looks like we've got cube root of 3, 3, 3, 5, and then we got 12 x's, which I do not want to write all those 12 out. You can if you want to. I'm just not going to do that. And y to the 7th. All right, so let's take a look and see what this looks like. So we've got all of this mess. Okay, so we need cube root, so 3 of these to come out as 1 on the outside. So I'm first looking at these 3 3s, and so I see that a 3 is going to come out. The 5 gets left under there, and so if I want to, I can just go ahead and put that here, cube root of 5, just sit there. Okay, what about the x's? 12 divided by 3 is 4, which means 4 groups of 3 x's can come out completely. And so I'm going to get x to the 4th power to take care of those x's. And if you actually wrote them all out, 12 of them, you'd circle 4 groups of 3, and you'd wind up having 4 x's right there. But you can see how that's a lot quicker. How many groups of 3 can I take out of 7? Well, 3 doesn't go into 7 evenly, but 6, it does. So I could take 2 groups of y's out, which is going to amount to 6. And then you got 1 extra one that's going to bring it up to 7. So that 1 extra one is going to go into the cube root over here. Okay? So now let's see what we've got. This is actually the simplified answer right here, even though I've got a gap here. This is actually the simplified answer. So our answer for this one is 3x to the 4th y squared times, and I like to use a little space, the cube root of 5y. All right? That one looks pretty good. Now, let's try one that is going to be quite intimidating to a lot of students. And that's going to be this one right here. I mean, why not make things difficult? The 4th root of, here we go, 6, 4, 8, 0, x to the 5th, y to the 14th. So why do I make things difficult? I want you to see that really nothing is beyond you. There's nothing that you can look at and say, well, that's too hard, I'm not doing that one. No, this is not too hard. It's not too hard at all. I'm going to change my marker here and get one that's hopefully one I can write with a little better. All right, so here we go. Let's break down 6480. So we're going to start with 648 times 10. I mean, you might as well. The 10 is going to break down into a 2 and a 5. All right, let's do 648. Let's try and break this down into 8 times something. And why do I think it's 8? Well, if I do 648 divided by 8, I get 81. So I'm going to do 8 here and 81 there. 8 is, as we've seen before, 3 2s. 2, 2, 2. Don't let anybody tell you that you can't do that, because if they tell you you have to break it down into 4 and 2 or something like that, no, you can just do it immediately. I mean, why should you do something that creates more work when you can already just break it down easier, like 81? I know that there's 4 3s that go into 81, because when I do 9 times 9, that's going to be 4 3s down there. And if I already know that, I mean, why not just go ahead and write 4 3s down? I mean, might as well. 3, 3, 3, and 3. Okay, so the hard work is done now. I've got the 4th root of 4 2s. 1, 2, 3, 4. 4 3s. 1, 2, 3, 4. 4 3s, 4 2s, a 5. And then x to the 5th. And then y to the 14th. Okay, so let's go ahead and draw a line up above those, because even though it looked difficult, it really was not, with a little bit of knowledge. Okay, so here we go. I need a group of 4 now because my index is 4. So I'm going to be grouping 4 of them. So I have 4 2s right there. So that single 2 out there represents 4 of them that were under there. I have 4 3s. Okay, so a 3 comes out. The 5 is left in. Okay, it doesn't have 3 more of them to make 4 of them. So over here on the side, I'm going to put 4th root of, and all my garbage I collect at the end is going to go here. All my leftovers, I should say. Okay, so how many groups of 4 can I take out of 5? Well, I can take 1 group of 4 out, but when I do, there's 1 left over. And that extra 1 that's left over, you guessed it, goes in there with all the extras. 14, 4 times 3 is 12. So I can take 3 groups out there. Okay, but what's left? 12, 13, 14. So 2 more are going to be left here after I take the 3 groups of y out. So those extra 2 are going to be shown right there with that fourth, with this radical right here, 4th root right there. So now I'm going to put a little dot there, and I have now my final answer. Well, not yet. 2 times 3 times x times y cubed, and then this guy trailing along, that's all the leftovers. All right, so let's clean that up one extra time. 6 x y cubed times, and here comes my leftovers, 4th root of 5x y squared. And if I'm going to submit this as my final answer, I'm going to make it look good. And that's going to be my final answer. And that's about as hard as they're going to get, unless you start throwing some extra variables in there. And you can handle extra variables like z or w the same way if you get more and more of them. But in Algebra 1 and Algebra 2, usually it's about this level right here. So that is simplifying radical expressions. Remember to like and share and subscribe to my channel. And we will see you guys later. Bye.